Now, doing the first exercise that makes use of these new concepts, we show that every n in n is t-finite. I am going to do the proof by induction. I know in a few videos ago I said that I was very skeptical of a proof by induction at this point in the development. I've since sort of convinced myself that it's not actually that big of a deal, that the proof by induction takes place in the meta language, which is just where any kind of good reasoning can be used, not in the object language, which in this case is the language of set theory, which has all of these constraints on it. So if that doesn't make sense, it's not too big of a deal, but I think that since I know that n is just the set of 0, 1, 2, so on, that it is just plain valid reasoning that I could prove that this property holds of 0 and so on with all of the other steps that involved in an inductive proof, and it will be a valid proof about n. So I'm going to do this by induction. To show that it holds for the base case 0, we need to show that it's t-finite, which means that we need to look at an arbitrary non-empty subset of the power set of 0. Now, 0 is the empty set. The power set of the empty set is the set of all subsets, and the only subset of the empty set is the empty set. So the only element that gets into the power set is the empty set. Okay, if X is to be a non-empty subset of that, it must just be equal to the set of the empty set. In that case, I claim that the empty set here is the submax element. Why is it the submax element? Well, to be submax is to not be contained by any distinct element in the set, but there is no other element in the set, so trivially in this case, the empty set is submax. Okay, on to the inductive case. Suppose that we know n is t-finite, we would like to show that n plus 1 is. Now, again, we want to just sort of flat-footedly spill out the meaning of t-finite for for this particular case, which is to have a non-empty subset of the power set of n plus 1. Now I would like to somehow relate this to the base case, which is about n. It tells me that if, say, S is a non-empty subset of the power set of n, then S has a submax element. So this is about P of n. Now, if I want to relate X to that and somehow exploit the existence of a submax element in an arbitrary subset of P of n, then what I would like to do is what's the difference between P of n plus 1 and P of n? P of n plus 1, certain of its elements have n in them, right? Because n plus 1 just is the set of all numbers 0 up to n, and we take arbitrary subsets of that, so some of them have n in them. Now here, n is equal to all the numbers 0 up to n minus 1, if such exists, but just for the purpose of explanation, let's go with that way of speaking, then so none of the elements of P of n have n in them. They have at most n plus 1. So that would be the thing keeping me from talking about X as a subset of P of n, is that certain of X's elements may have n in them. So, to correct for that, and hopefully be able to relate back up to P of n plus 1, but to basically make the first step, let's define this set, which is constructed as, so to speak, taking some x in x and subtracting off n from it. So now we must in fact be dealing with a collection of elements in P of n, and now I can use the inductive hypothesis on that. We know that y must have a submax element, call it U, I claim that this U is related to the submax element in X. Namely, U must have come from deleting n out of some x in X. And I claim that this X is in fact the submax element of X. Why is that? Well, I'll argue it this way. U being submax means basically that nothing else, nothing distinct from it contains it, so that it must have some element that nothing else has, and that therefore X also has that thing, and the property will carry back over to X, that there is something that it has that nothing else does. That's basically my method and thinking about how to do this. So, to do that, I'll pick an arbitrary v in X that is not equal to little x, and I will argue that v does not contain X. How do I know this? Well, if we subtract off n from v, we get ourselves an element out of y. Now that means since u is submax, u contains some element which is not contained in v minus n, and also this element a cannot be equal to n, and that's because we're dealing with things in P of n. As I argued before, none of those have n in them, so this a cannot be n. Now, when we go back to big X and little x also, whatever that element was in u, it must also be in X, right? Because X is only bigger than u. U was, after all, X minus n. So whatever that element was, it must still be an X when we go back to the bigger set. And it didn't get to enter V, right? When I go from V minus n to V, A is not in V, because all I did was I possibly permitted it to have n this time, but I know A is not equal to n. So here we have it. A is in X, it is not in V, so U is not a subset, X. X is not a subset of V, and since this is true for all choices of V in big X, therefore X must be submax. It has a submax element. Sort of looking back and remembering what we wanted to do, well, that's exactly what we wanted to do, right? This is the inductive part of the argument, and I just showed that an arbitrary choice out of P of n plus 1 has a submax element, and that's the end of the proof.